Two, one. Lah. Okay. Okay, good morning, distinguished presenters, valued delegates, ladies and gentlemen. I am Muhammad Aslam, your chairperson for this Icoget Ps1 R2 session. Together with me today, I have Nur Ashraf Mahir, who will be assisting me to ensure that the session runs smoothly. We will be beginning the session shortly. So I would like to request everyone to put your microphones on silent mode. If you wish to ask any questions, please use the live Q&A session chat box. Thank you very much for your kind cooperation. So we now have the privilege of listening to Raja Rajaswari from University Technology Petronas on experimental investigation of the effects of temperature on the morphological characteristic of geopolymer binders. Please join me in welcoming Rajesh to the podium.
Good day to everyone. My name is Raja Rajaswari from University Technology Petronas. I'll be presenting on the effect of temperature on the morphological characteristics of the geopolymer binders. My presentation consists of introduction, geopolymerization concept, objective, methodology, results and discussion, and finally the conclusion. We will move on to the introduction section. What is geopolymer? Geopolymer is a polymeric silicate oxide aluminate structure known as alkali activated alumina silicate cementitious material. The major raw materials for a geopolymer formation can range from fly ash, slag, and rice husk, which have high silica content, and also clays like kaolin, which has high alumina content. Besides that, alkaline activator such as sodium or potassium hydroxide or sodium and potassium silicate can be used as an alkaline binder for the formation of geopolymer cement. Next will be the concept of geopolymerization. There are three critical steps of geopolymerization that ultimately form geopolymer gel. The first step is the separation or dissolution of silicon and aluminium when aluminosilicate in touch with sodium hydroxide. Second step would be the transportation or the orientation when the particles move in sequence. And third is the polycondensation or chemical reaction to form the geopolymer cement. Here in figure 1, it shows the geopolymerization process. Here, aluminosilicate source reacts with the alkaline binder, which is sodium hydroxide and sodium silicate, and the aluminate and silicate separates or dissolutes in the solution. After going through a speciation equilibrium, the silicate is transported or orientated to form the gelation. And this gelation will reorganize in sequence and react with the chemical or polymer for the polymerization and hardening of the geopolymer slurry. The objective of this research is to investigate the effect of temperature on the morphologic characteristics of geopolymer cement. Looking into the methodology, there are three methodologies that have been implied in this preparation of geopolymer cement sample. First is the slurry preparation, where the slurry is prepared according to the testing methods of API 10B R2. Speed mixer has been used with different range of speed for 50 seconds to mix the solids and liquids together. All liquids and mixed together before solids is added to the geopolymer system. Next, the prepared geopolymer slurry is then poured into a polished and greased molds and cured in water bath for 24 hours. Once the sample has been cured, the samples are taken out and dried and further crushed to make it into a powder form. The crushed powder form samples were then sent for FISAM testing. The cement samples were prepared with accordance of API 10B R2 testing procedures. The parameters that have been used for the geopolymer sample is with 11 ppg, 13, 15 and 17 ppg samples. The temperature that has been used for testing the geopolymer cement is at 30, 60 and 90 degrees Celsius. Here, this figure shows the cured geopolymer cement samples that has been taken out and dried from the water bath after curing it for 24 hours. We will move on to the results and discussion session. Okay, figure 3 shows the 300 times magnification of fly ash sample tested at 30 degrees Celsius. These fly ash samples consist of cenospheres at magnetic sphere. Cenospheres generally forms a large ratio of the lightweight elements due to their hollow characteristics. Magnetic spheres are the solid spheres containing the iron crystals covered by amorphous alumina and silica that actively participate in the geopolymerization process. As shown in figure 4, 100 times magnification of FISAM of geopolymer samples of 11 ppg, 13 ppg and 17 ppg tested at 30 degrees Celsius. It can be seen that at 11 ppg and 13 ppg, there are hollow spheres exist on the mixing of the geopolymer slurry. Meanwhile, in 17 ppg, the reactions are more complete compared to sample of 11 ppg and 13 ppg. The samples cured at 30 degrees Celsius clearly shows there is a less amorphous gel, and large particles of fly ash sample still did not completely react with the silicate, especially at lower density. Figure 5 shows the FISAM of geopolymer sample at 15 and 17 ppg at 60 degrees Celsius. Vast difference can be seen compared to the sample tested at 30 degrees Celsius. Here, in 60 degrees Celsius, better reaction can be seen compared to samples taken at 30 degrees Celsius. Fly ash has almost completely reacted with the silicate gel, and morphological changes can be seen where the silicate gel or the dissolution of the silicate and aluminate leads to the formation of gel type of aluminosilicate gel covering the fly ash sample. Here in figure 6, it shows the micrograph of the samples cured at 90 degrees Celsius at 11 ppg, 13 ppg, 15 ppg and 17 ppg. At 11 ppg and 13 ppg, hollow spheres can be seen and there's no dissolution of silicate regardless it has been tested at an elevated temperature. Meanwhile, 15 ppg and 17 ppg at a temperature of 90 degree shows a dissolution of the silicate and alumina gel covering up the fly ash sample and forming a gelation properties. Samples at 90 degree indicate that the geopolymerization of fly ash was extensive and full mode as a compact structure, even though unreacted fly ash can be seen. Highlights of this test is on 17 ppg cured at 90 degrees Celsius, as there was a surface continuity resembling a gel type of the reaction product. As a conclusion from this research, temperature plays a significant role as a reaction accelerator. Unlike Class T cement, geopolymer has a certain valid reaction temperature due to its geopolymeric structure. It can be clearly seen that the reaction of fly ash with the silicate activator is best at 60 degree compared to 30 degrees Celsius and 90 degrees Celsius. This is because at a temperature above 60 degree, the polymer chains break down and the reaction is retarded before the silicate gel matrix is equally distributed. Many articles have supported that the optimum temperature for geopolymer cement is at 80 degrees Celsius. That's all for my presentation. Thank you.
Okay, thank you very much, Rajesh, for the informative paper.
Okay, thank
So
you.
we now like to invite questions from the members of the audience. Dear delegates, please use the live Q&A session chat box to write your questions. Okay, seems like there is no question from the live Q&A. So I have one question for you, Rajesh. In your explanation, you have mentioned that you have clearly explained about the effect of temperature, but seems like when you varied the the density, there is also the effect, the changes on the morphological of the cement binder, right? So could you explain? Please explain why is that happen?
Okay, thank you, Aslam, for your question. Okay, this is because of the density and temperature. Actually, the density has an effect also together with the temperature. But if you see for cement, compared to density, the temperature has significant effect because since it's a geopolymer and it's not a class G cement, geopolymer are highly temperature sensitive. And even though the density also plays an important role because the material that have been included in the to change the density are different for a low, medium, and high temperature. So if you can see the at high density, which is like 17 ppg, weighting agent is added. So the weighting agent could also be a factor to give a strength to the geopolymer and the morphological changes. So this is vice versa where density and temperature are both playing a significant role in the morphology of the geopolymer cement.
Okay, thank you, Rajesh, for very good, very clear explanation. So I think there is no question from the floor. So I think that's all for this session. Thank you, Rajesh. And now we will move on to the next speaker.
Okay,
Okay, thank
thank
you.
you.
Bye.
Bye.
Okay. Kita tunggu. Do we need to wait? Oh no. So now I would like to request for the next presenter, which is Nurul Aimi Ghazali from the University Technology Mara, Malaysia, and the University of Tokyo, Japan, on the title The Effect of High Temperature Environment on the Rheology and Filtration Properties of Reservoir SPP tannin lignosulfonate as bio-based deflocculant in water-based drilling fluid. Please join me in welcoming Nurul Aimi.
Assalamualaikum and a very good day to everyone. I am Nurul Aimi from UiTM. Today, I will be presenting our research work entitled The Effect of High Temperature Environment on Rheology and Filtration Properties of Reservoir tannin lignosulfonate as bio-based additive in water-based drilling fluid. As for introduction, I will discuss on drilling fluid properties, specifically water-based drilling fluid. Drilling fluid is a live hood of drilling rig system that allow this circulation to serve several functions such as hole cleaning, transport the cutting to the surface, and preserve the stability of the wellbore. Our research is focusing on water-based drilling fluid, which mainly comprise of water as the base fluid, bentonite from the clay group, and the additive. Due to high surface area of bentonite with a negative zeta potential, it is actually a stable colloid suspension in water. But dealing with bentonite is very crucial since it is sensitive with the formation environment. Flocculation is also a common occurrence for water-based drilling fluid. It's happened when the positive charge of the edge clay layer attracted to the negative charge on the surface of clay and form a clump clay suspension. There are three conditions where drilling fluid is susceptible to flocculation. The first one is high solid content, which is commonly active solid content. The second one is a high electrolyte, such as salt. And the third one, high temperature. It was found that at high temperature, more than 120 degrees C, the flocculation sharply increased and the clay particle bind together to form a floc particles. It also creates an open network that induces the filtration loss. In this situation, flocculation is normally added to control such situation. It can neutralize the charges at the edge particle and deassociate the particle. The flocculant must be able to sustain at temperature more than 120 degrees C, as many additives prone to degrade at this temperature. In the past research, linosulfonate was introduced to replace cubicotannin as the flocculant, that also known as thinner. It is because the hydroxyl and ether group has the ability to absorb on the clay particle, while the carboxyl and sulfonic acid improve the technical performance and stabilize the colloid particle. Main drawback of cubicotannin and linosulfonate is low thermal stability. It not able to perform at high temperature, which is more than 225 degrees Fahrenheit. It also not perform in higher salt concentration. Other flocculant, for example, phosphate, will revert to flocculant at high temperature more than 180 degrees Fahrenheit. So to encounter thermal stability problem, ferric and chromium was introduced to improve the temperature resistance. Chromium is always chosen by the additive manufacturer due to high thermal stability, but it is not ecologically friendly. Therefore, the aim in this study is to eliminate the use of chromium by developing an eco-friendly RTLS, the flocculant with high temperature stability for water-based drilling fluid. This slide shows the process of disulfiram being extracted from the waste of conventional charcoal production, and currently the bark was left to burn and sold as fertilizer. So our project member used the bark to extract the tannin, which was done in frame. They have done a study specifically on tannin itself as additive in drilling fluid, and it's proven to work. For this research, we cross-linked the extracted tannin and linosulfonate through this process to further improve the thermal stability. We use a chrome-based deflocculant and tagged as ICD in this presentation to compare the performance of our synthesized additive. 4 different concentration of RTLS and ICD used in this study, and all samples were aged at respective temperature for 16 hours. Plastic viscosity is a primary function of viscosity. Ideally, the addition of the flocculant does not reduce the PV. PV sometimes can increase due to the amount of content in drilling fluid. Thus, there are small fluctuations in PV. But the high temperature condition does affect the PV as it gets higher at high temperature. Temperature agitation tend to allow further hydration of individual clay platelet and increase the viscosity as the volume increase. Small effect can be seen when the particles are large and relatively unhydrated. High yield observed at high temperature and reduced as the temperature reduced. 2 conditions that will influence the yield point. The first one is electrical interaction of solid, which can be controlled by chemical treatment, deflocculant. And the second one is mechanical interaction, controlled by solid or polymer. Clay platelets that link to each other increase the yield point when it is flocculated. Chemical treatment will neutralize the clay platelet and reduce the yield point, but once the condition is accomplished, further addition of chemicals does not reduce the yield point. So they have optimum. They have the optimum concentration to work best to produce the good yield point. Removal of colloid solid is needed when we wanted to have a further reduction of yield point. A desired characteristic of filter cake, which is good for filtration, is thin and low permeability. At temperature 177, it's look like both RTLS and ICD can't reduce further the thickness, but it works at temperature 149 and below. As mentioned earlier, the flocculant able to reduce the fluid loss as a secondary function in drilling fluid. When the temperature increases, the fluid loss will increase due to reduction in viscosity of filtrate. At high temperature, the fluid additive also prone to degradation, but slight changes shows that the additive is still work. Experiment data were fitted to Herschel-Buckley model using origin. Tau represent the yield stress and K as the consistency coefficient and N as the flow characteristic exponential. All these data present a good linear relationship as all the coefficient relationship R square are around 1, meaning that the model fit well with the experimental data. The fluid behave like pseudoplastic with a low value of N. As can be seen by all the RTLS sample, the fluid belong to Newtonian fluid when the N is equal to 1 and tau is equal to 0, which can be observed in ICD. This figure shows the morphology of filter cake under FISM EDS. It was dried before running for this analysis. The left sample is the bentonite slurry and the right sample is the bentonite slurry with additional RTLS 1.0 weight percent. Both filtration were carried out at the temperature 121 degrees C. Adding RTLS to the bentonite resulted less porous structure and smooth morphology with no obvious fractures compared to bentonite slurry alone. This morphology and analysis confirmed the newly synthesized additive improved the fluid loss by reducing the open network used due to flocculation. The EDS counted the aluminum and silicon because bentonite is a natural smectite clay that is formed from the octahedral layer of these two elements. The increase of percentage on element C appear because RTLS that associated to the bentonite structure. This suggested that RTLS play important roles in improving the rheology and reducing the fluid loss. The laboratory drilling fluid as a conclusion, the laboratory drilling fluid were designed to simulate high temperature environment through aging at high temperature. The thinning performance with newly synthesized RTLS in water-based drilling fluid was evaluated by rheological properties and filtration properties assessment. Reservoir tannin lignosulfonate improved the rheology and filtration properties of water-based drilling fluid. It outperformed the ICD, industrial chrome-based deflocculant. RTLS 0.5 weight percent is sufficient to improve the performance of rheology and filtration, as the site of the edge surface area is small with respect to the overall surface area, thus a low concentration is very significant. FISM EDS analysis confirmed that RTLS is sufficient at producing a smooth morphology with less porous filter cake. This environmentally friendly and non-toxic deflocculant might replace the chrome-based deflocculant that are currently in use for drilling borehole. Thank you.
Okay, thank you very much, Nora Aimi, for the very wonderful presentation. So now we'd like to invite questions from the members of the audience. So dear delegates, please use the live Q&A session chat box to write your questions. Okay, I think there is while waiting for the question from the floor, I think I have one question, maybe two questions for the Nurul Aimi. Actually, I'm really my research area because previously I have done quite a number of research in green fluids. So, but this is new thing for me for when you did your research on focus on deflocculant, right? So, just a simple question: have you compared the performance of your product, which is the new product that you are doing in your research, with the commercial one?
Yes, in the slide that I presented,
Mhm.
there is a two graph for each result. For example, the plastic viscosity. The first on the top is we added our synthesize, which is RTLS, and on at the bottom of the slide is ICD, which is industrial chrome-based deflocculant. So some we didn't name it because it was belong to a certain company due to
Okay, alright.
confidentiality. So, but the deflocculant that we use, it has a chrome. It is a chrome-based deflocculant. So we did compare between these two analysis
All right. Okay.
performance.
Okay. But another next one. Just a simple question. For the questions. Oh, I think. Okay. For the next one. What's the stage of what I call your research of this product? Is it ready to be commercialized, or maybe it's still in the beginning of the?
Yeah, it's still in the beginning. We haven't because for to commercialize, we need to consider on the mass how to say the production of
Yeah.
the tannin itself, the availability. But now we are working with the team in our university to produce the tannin for the application of drilling fluid. Now it's still in the beginning of the study.
All right. That's good. Okay. So let me see if there is any question. So I think there is no question from the floor. So I think so. Thank you, Amy,
Okay, thank
for
you, Dr. Aslam.
participation. All right.
Okay.
Okay. Have a nice day.
Yeah.
Okay. Now we have finished with the second part. So now let's continue with the third paper for today's session. So I would like to welcome Omar Ishtiaq from University of Technology Petronas with his paper on incorporation of nanofillers onto nanocomposite coated propellants for improved mechanical strength for effective hydraulic fracturing.
I welcome you all listening to this presentation. My name is Umair Ishtiaq, and the title of my presentation is High Strength Glass Beads Coated with Carbon Nanotubes (CNT) and Reduced Graphene Oxide (RGO) incorporated into urethane coating for improved crush resistance for effective hydraulic fracturing. My presentation outline will be starting with background, followed by introduction, research gap and problem statement, objectives, methodology, results and discussion, and finally conclusion. So starting with the research background, shale production is gradually shifting into deeper and tight, low permeability formations at high temperature and pressure conditions that poses a projected extraction challenge to oil and gas companies. Advances in hydraulic fracturing coupled with horizontal drilling has successfully produced vast amounts of hydrocarbons. To keep this production momentum ongoing, continuous advancement of hydraulic fracturing technology is of paramount importance. Propellant, being one of the fundamental components of hydraulic fracturing process, offers sufficient room for its improvement and advancement. Now coming towards a general depiction of hydraulic fracturing process and propellant injection. After drilling, casing insertion and perforation, hydraulic fracturing fluid is injected at high pressure that causes fracture propagation as can be seen in figure A and B. After the creation of these fractures, propellant is injected into these fractures that prevents these fractures from closing in. Now coming towards introduction, silica sand is one of the conventional propellant that is one of the main constituent of hydraulic fracturing fluid. The main purpose of propellant is to keep the hydraulically induced fractures open and conductive. That means that the hydrocarbon can easily flow through the propellant pack by acting as a mechanically small support particle that provides conductive pathway for hydrocarbons to flow from the reservoir to the wellbore. The propellants can be classified into three basic categories: low strength propellants, medium strength propellants, and high strength propellants. Since past few years, various polymeric coatings are applied on silica sand propellant in order to enhance their mechanical strength. Now coming towards research gap and problem statement, as already stated that shale production is gradually shifting at greater depths into tighter formations at elevated temperature and pressure conditions, at which the fractures induced by hydraulic fracturing exert high closure stresses, making the sand unviable as conventional propellant. Propellant sand is crushed. That leads to detrimental fine generation and unwanted loss of fracture conductivity, which means that the fines choke the propellant pack. As already stated that silica sand as propellant, various kinds of polymeric coating has been applied on it, but these polymeric coating has certain limitations. That is, when the temperature is greater than 70 degrees centigrade, the glass transition temperature of most polymeric coatings is reached. That softens these coatings and reduces the mechanical strength of the propellant pack. So in order to address these issues, various additives were added into these polymer coatings, such as glass fibers, nanomaterials such as aluminum oxide, zinc oxide, magnesium oxide, and in this work we will investigate the inclusion of carbon fiber in the form of CNT and graphene oxide to improve the mechanical strength of the polymeric coating. So now coming towards the objective, the first objective is preparation of 0.1, 0.5 and 1 weight % concentrated dispersed solution of CNT and graphene oxide, each mixed with aqueous polyurethane solution. The second objective is coating the glass beads propellant by the prepared solution by means of dripping. The third objective is crush test analysis of the coated glass propellants by universal testing machine UTM. And finally, to characterize the coated glass propellant morphology and fiber dispersion by means of FESEM analysis. Now coming towards the methodology, the first thing is solution preparation. As already stated that we will prepare 3 solution each of CNT and graphene oxide having concentration of 0.1, 0.5 and 1 weight % mixed and sonicated, followed by polyurethane solution addition and again mixed and sonicated to produce a well dispersed polyurethane CNT or graphene oxide solution. This whole process will be done for the preparation of graphene oxide plus polyurethane solution. When this well dispersed solution is prepared, then this is applied on the glass bead propellants simply by placing these glass bead propellants on a sieve paper and adding this solution dropwise onto them. So here we can see that we have this glass bead propellant which is coated with polyurethane coating incorporated by nanofiber such as CNT or graphene oxide. This glass bead propellant is cured at room temperature for 1 hour. Now coming towards crush test analysis by UTM Universal Testing Machine, these coated propents are placed in crush cell. Vertical load is applied at a constant displacement rate of 0.5 mm per minute until it reaches the target stress level of 4000 psi. Then this applied load is removed and the crush sampled is sieved to separate the crushed propent and the fines. Now coming towards the results and discussion, as already stated before, that these glass beads are coated with 3 concentrations of CNT and 3 concentrations of graphene oxide. So here in figure 6a we can see the pictures of the coated glass bead propents. Now the crush test results. Here we have this crush test results, and here we can see that when the glass bead propent is coated with CNT polyurethane solution, there is increase in the compressive strength of the propent grain by the crush test analysis. When the concentration is 0.1, we can see that there is significant increase from the uncoated glass bead propent grain. And when the concentration is further increased to 0.51 weight%, there is increase in the compressive strength. When the concentration is further increased to 1 weight%, that the carbon content is increased, so there is a decrease in the compressive strength. For the fine generation, we can see that as the carbon content is increased, there is a decrease in the fine generation. Graphically representing this, as already stated before, that when the glass propent grain is coated by 0.1 weight%, we see an increase in the compressive strength of the propent. Further, when the carbon content is increased from 0.1 weight% to 0.5 weight%, there is further increase in the compressive strength of the propent grain. But when the carbon content is further increased to 1 weight%, there is a decrease in the strength of the propent grain. Now, this increase in the strength of the propent grain is due to the inclusion of carbon fiber into the polyurethane coating that effectively distributes the applied vertical load stress. But this concentration has a certain limitation, is a threshold value. If the concentration of the carbon content is increased more than 0.5 weight% to 1 weight%, we see a decrease in the compressive strength. Now this decrease in the compressive strength is attributed to the agglomeration of the carbon nanotubes due to the presence of van der Waals forces between them. Now coming towards the fine generation, as the carbon content is increased, we see sharp decrease in the fine generation. This is attributed to the creation of a web-like structure around the propent grain that prevents the fines, that encapsulate the fines and prevents it from going out of the propent body. Now coming towards the results of the propent coated by graphene oxide. Similarly, here we can see that we have the glass bead propent coated with 3 concentration of graphene oxide, 0.1, 0.5 and 1 weight%. Now coming towards the crush test analysis, here we can see that when the concentration of the graphene oxide is increased from uncoated to 0.1 weight%, we see increase in the compressive strength. When the carbon content is increased further from 0.1 to 0.5 weight%, we see a decrease in the compressive strength, and followed by when the carbon content is increased further to 1 weight%, we see a further decrease in the compressive strength. For the fine generation, as the carbon content is increased, we see a increase in the generation of fines. graphically representing that when the carbon content is in the carbon content, like the graphene oxide is basically increased from uncoated to 0.1 weight%, there is an increase in the compressive strength of the propane grain. Now this again attributes to the inclusion of the carbon fiber that well distributes the effective load stress. But as the concentration is increased from 0.1 to 0.5 weight%, we see a decrease in the compressive strength, and as the concentration is further increased to 1 weight%, we see further decrease in the compressive strength of the coated glass bead propane. Now this decrease is again attributed to the agglomeration of the carbon content of the graphene oxide layers. Now this agglomeration is mainly attributed to the presence of more profound hydrogen bonding present between the graphene oxide layers. For fine generation, we can see that as the carbon content is increased, the fine generation is also increased. So here it is depicted that this graphene oxide does not create an effective web-like structure that encapsulate and contains the fines inside the propane body, and the fines can be easily released from the propane body. Unlikely in the case of CNT, that the CNT was effectively forming a web-like structure and was effectively encapsulating and containing the fines, and the fines were not being released even when applied load was increased. Now coming towards some FESEM images, here we can see that the presence of, here we can see the structure of the crushed propane grain, and then here we can see the presence of carbon nanotubes CNT present into the propane body, into the propane grain, which is like in a very well dispersed format. So now coming towards the conclusion. So here we can conclude that the mechanical strength of the glass bead propane was enhanced by the incorporation of both CNT and graphene oxide as reinforcing fibers. But here the increase in the CNT and graphene oxide has certain limitation, has certain concentration limitations. That is, if the concentration is increased more than this threshold concentration, we see a phenomenon of agglomeration. In CNT, the phenomenon of van der Waals forces come into play, whereas in the case of graphene oxide, the more profound phenomenon of agglomeration through the presence of hydrogen bonding comes into play. So in the case of CNT plus polyurethane coating, the CNT provides a web-like structure around the propane grain that effectively encapsulates and prevents the fines from releasing the propane body, whereas this phenomenon was not witnessed in the case of graphene oxide polyurethane coating. The fines were basically generated and were easily released from the propane body. So the agglomeration of CNT and graphene oxide fails due to the agglomeration of CNT and graphene oxide. The applied load was not effectively distributed. That leads to propane crushing and fine generation. The best optimum concentration for CNT was 0.5 weight%, and for graphene oxide the best optimum concentration was 0.1 weight%. So we can conclude that in terms of performance, CNT performed better as compared to graphene oxide. It well distributed the applied load stress, as well as it also created a web-like structure that effectively encapsulated and prevented the fines generated due to crushing to release from the propent grain. So this concludes my presentation. Thank you very much.
Okay, thank you very much, Hisham, for very comprehensive presentation. So we now would like to we would like to invite questions from the members of the audience. So the delegates, please use the live Q&A session chat box to write your questions. Okay, ladies and gentlemen, due to some unforeseen technical problems, we have to move on to the next paper at the allocated time slot. Right. So I think without further ado, let me invite Mr. Muhammad Jalil to present his paper on fracture connectivity mapping of the basement using advanced attribute, a case study from Peninsular Malaysia field.
Hello everyone, hope you are doing well. Since we are still in the pandemic situation, hopefully you will always take care of yourself and your family. Today, I am Mohsen from Petronas who would like to present on the topic titled Fracture Connectivity Mapping and the Basement using Advanced Attribute that we take a case study from Peninsular Malaysia field. I am the main author of this paper and assisted by my colleagues as co-authors, which are Anchinti, Yusuf Karel Amin, Rosalie Daniel, Shaini, and Rahadian Anwar. My presentation will touch on the problem statement, technology overview, concept and methodology, followed by the introduction of the field study, the result of the application of advanced technology, and the conclusion. Last but not least is my acknowledgement to the party that helped me to present on this topic. Firstly, we will understand on the problem statement. It is a challenging task to explore or analysis at the basement field area, especially when we come to the prospect evaluation stage, whereby we need to work with limited information available. Especially in Malay Basin, the potential of basement field is not fully explored because only few numbers of successful and unsuccessful drillings have been done. Other than that, the seismic attributes in the market are mainly developed for classic environment and may not suitable to evaluate for basement prospect. Ladies and gentlemen, do you know that we are in the Petronas are developing our in-house technology to help our geoscientists for doing their jobs? One of the technology is called as a network tortuosity decomposition, or we call that as a NTD. One of the purpose of NTD is to map fracture connectivity, intensity, and show possible path for fluid flow. In addition, NTD also can decompose the fracture network into its orientation and quantify the fracture azimuthal variation of the detected fracture network. And this will ultimately help in the well trajectory planning. Another benefit of NTD is it will produce one rows plot as output to show the density of fractures for all orientations. So from here, we can know which orientation contributes the most fractures. Now we come to the next question. How is the NTD works? I will explain on the workflow and the algorithm of it. First, NTD operator will divide our seismic data to slice by slice and then make a M times M matrix from the seismic data. Next, come to the identification of fracture or connectivity. The tool will check the connectivity for all directions starting from 0 degree to 360 degrees as shown by animation. The green boxes shows the cells location that are used to determine the fracture orientation. So now he will calculate the fracture to see the fracture between the 0 degree to 360 degrees. Hereby, the red dot is the analysis point. The NTD engine will scan the amplitude surrounding it and define whether that point is a fracture or not by using this equation. This equation contains of three conditions and must be met to mark that point as a true. For instance, the amplitude at x1 plus amplitude at the x5 minus 2x3 must be bigger than amplitude at the analysis point. And this is the second and this is the third conditions. Again, if all conditions are met, so that the point will be marked as true. And the similar workflow will be repeated at these blue cells at 0 degree to ensure that line is a fracture or not. After it's done at 0 degree, it will continue to scan at the next 22.5 degree until 360 degrees to analyze on the fracture on the other direction. During the NTD development, we will use synthetic data as technology validation. And from the input data, we can see lots of fractures, but we have difficulties to distinguish whether the fractures are connected or disconnected. We are also cannot define the direction of dominant fracture. And these are the inputs from the NTD. And from here, we can conclude that these are the only fractures that are at least 3 points connected. Yellow color shows a higher intensity of fractures, while the blue has less intensity. And these are the possible path for fluid flow. And this is the fracture density output from the NTD that shows that the most of the fractures at the 90 degree and 270 degree orientation. This study was performed on the field A in the Malay Basin to map for the fracture network connectivity and identify the potential area for exploration. And this field A consists of a granitic basement and few wells here that have been drilled and penetrated its top of basement. For instance, well 1 has been drilled up to 190 meters below the top of basement and content of oil and gas shows, while the well 2 has been drilled that penetrate below the top of basement and has the oil show. The kitchen area is located at the south, and the field also has one major fault along this northeast southwest direction, which is believed to be the hydrocarbon migration path. Figures on the left shows the NTD result that extracted the 5 meters below the top of basement. The whitish zone indicates that no connectivity, while the black defines the fractures. And we can see at this level that the 5 meter below top basement, there is not so much fractures can be observed. Thus, we can assume that this area can be as a good seal. We go down to 20 meters below the top of basement, and this is the result of NTD. That NTD shows more fractures. And from this rose plot information, most of the fracture orientation is at the northeast southwest direction. And also from here, NTD also can show that there is high fracture zones at the well 1 location, and this area is highly compartmentalized. And due to the structure trap, this explains why the hydrocarbon show is only showing at these locations, well 1 and well 2. Other than that, then we come to the what are the things that NTD help. NTD also help in identification of the potential zone. So now we can see that we have 2 zones here, zone A and zone B. These 2 zones have the high fracture density. And from the previous petroleum system study, that it indicates that the kitchen is located at the south of this field, and the northeast southwest major fault is believed as the hydrocarbon migration path. Since A is located near the fault, has higher potential to accumulate hydrocarbon as compared to zone B. And this is also supported by the oil show at the well 2, that the NTD result also display determination at the major fault at the northeast of the zone A at this area. So we can see from this area, this is one major fault here, and this is another fault, and this is the point where these 2 faults has been terminated. And we also calibrate the NTD result with the well calibration. If you remember, as mentioned before, the well 1 content of the hydrocarbon show, and here is the mark log of well 1. And from the mark log, there are 3 fractures zones and marked with the zone as fracture 1, fracture 2, and fracture 3. And from here, we can see that NTD result observe the true fractures, which are fracture 2 and fracture 3. One more benefit of NTD, it will show the fracture at the different orientation. For instance, this fracture 2, the direction is at the 5 degree, 140 degree, and also 27.5 degree. While fracture 3, the direction is at 27.5 degree azimuth. This information is important to help engineer to plan the drilling trajectory. So this is the conclusion. NTD attribute is a tool to map the fracture connectivity, density, and the fracture orientation. And in this field study, NTD shows that the most of the fracture network is at the northeast and southwest trend. By integrating the petroleum system modeling result, NTD able to identify two potential zones, which are Zone A and Zone B, and also supported by the nearby well result and the basement structures. Calibration with the well data, for example, the well 1, also shows that NTD predicts the fracture zones accurately. And last but not least is the NTD gives information on the fracture orientation, and this will help engineer to plan for the well drilling trajectory. Here is my acknowledgement. We thank to the management of Petronas for their permission to publish this work, and this could only be achieved by the dedication and effort of the many professionals that involved in this project. With that, I would like to thank for your attention to this presentation and see you again. Thank you.
Okay, thank you very much, Mr. Mohsin, for the very good presentation. Now we would like to invite questions from the members of the audience. So the delegates, please use the live Q&A session chat box to write your questions. Okay, I think there is two questions from Muhammad Abdullah Ayub. Okay, Mr. Mohsin, the first question, what are the features of this synthetic data that you use?
Again, what
are the features of the synthetic data that you use?
What the features? So we have this synthetic data that given from that shared by one of our partners, and this synthetic data shows that there one is a fractures features, and from there we try to use our tool to see whether that our technology can help to show the correct fractures or not. Yep.
Okay, thank you. And the next one, the question asks, how did you validate the results of the potential hydrocarbon identified using this approach?
Until now, we still have a limitation on this technology, because to identify the hydrocarbon, to measure whether the area contain of hydrocarbon or not, we must know that the fracture is open or closed. So up to now, we just can conclude that this technology just only can shows the feature of the fractures, and we cannot distinguish we cannot distinguish between the fracture is open or closed yet. But when we try to observe from the other technology outside that available in the market, there are still no technology that can identify whether that fracture is open or closed yet. Yeah.
Oh, and then there's another continuation
Okay.
question. Any simulation work to confirm that?
We have applied in the several field data, and for the calibration also we have calibrated with many wells to calibrate our fractures with the fracture zones that that shown from the well fracture markers.
Okay.
So when we calibrate with our technology with the well data, so we can conclude that our technology can predict almost 70% or 70 to 80% the fractures is correct.
All right, I think okay, that's all the question from the floor. And okay, I think that's all. Okay, thank you.
Thank you. Yeah.
Right. All right. Now we finished with the fourth session. So now let's continue with the next presenter. Okay, we now have the privilege of listening to Mr. Hisham Abdullah from University Technology Petronas on a paper titled Experimental and Modeling Study of the Synergetic Effect of Brine Composition and Surfactant Type on Exhaust Methane in Merciless Shale. Please join me in welcoming Mr.
Today we
Hisham.
will present for you a method to assess capillary pressure water saturation relationship in gas shales using relative humidity chamber. Due to the development in hydraulic fracturing and horizontal drilling technologies now, the production of gas from shale reservoirs became possible despite their ultra permeability. However, they are often associated with a low permeability, which is considered very tight. As we see in the charts, most of the shale gas plays in the United States, they're having a permeability lower than 0.1 millidarcy. And that is often associated with very tiny pores that cause a retention of hydraulic fracturing fluid due to the capillarity. And we need to find a very precise method to assess capillarity in these tiny pores and to assess the capillary pressure relationship with the water saturation in these pores also. Normally, in oil and gas industry, we are using Young-Laplace equation to describe the capillary pressure as a function of the pore radius and the interfacial tension between two immiscible fluids, and also the contact angle between the fluid and the surface of the pore. As we can see, the capillary pressure is inversely proportional to the pore radius. The smaller the pore, the higher the capillarity, and that is very obvious in gas shales because most of the pores are micropores less than 2 nanometer, which is by far very smaller than the conventional reservoir rock pores. And the assessment of capillary pressure is often carried out by some methods like porous plate method, centrifuge method, and these methods are designed to assess capillary pressure in conventional resources such as sandstone reservoirs, where the capillary pressure can reach to 3 megapascal only. But in unconventional reservoir, including gas shales, the capillary pressure can reach to 500 megapascal, which is very high, and therefore the conventional methods are not suitable to assess capillary pressure relationship in shales, including this porous plate and centrifuge method. They are not feasible to assess such high capillary pressure, and we need another method to do that. In this paper, we are assessing capillary pressure relationship using an approach that was previously, it was attempted by only 2 previous studies, but they have a drawbacks. These are the 2 only studies that attempted, as to the best of our knowledge, they attempted to assess capillary pressure relationship using a new approach, which is a relative humidity. And they have 2 downsides. They use crushed shale, which are not representative of the actual samples, and the process is very lengthy, and then it can reach to like a couple of months, and there is a mass loss of the sample during the process, which affect the accuracy of the results. We capitalize on these 2 researches that have been previously done, and we wanted to minimize their their downsides. We did take 6 shale samples from Marcellus Formation, Eagle Ford Formation, Mancos Formation, and from Wolfcamp Formation. And we assess the porosity of those samples using helium porosimetry, and that will be used an input in the further assessments. And this is the core of the work that we have done, which we utilize a relative humidity chamber to assess the capillary pressure relationship in these shale samples. We did 2 steps, which is imbibition test and drainage test, like the normal procedures followed in any capillary pressure test. First, we dry the samples in 105 degrees Celsius for 24 hours, and the dry mass of the shale samples is taken, and then we control the relative humidity in this container. We started from 10%, and then we noted the mass difference in our samples every 2 hours until we achieve a constant mass at each relative humidity level. And then we move to the next level, 20%, 30%, until we reach to 100%. And the drainage test was the opposite of the imbibition test, where we reduced the relative humidity in the chamber from 100% to 10%, and we noted the mass every 2 hours until we reach a constant mass. We determined after that the water saturation using the gravimetric saturation method, which we converted later into the volumetric saturation, and we determined the capillary pressure at each relative humidity level using Kelvin equation. And to make sure that our method is practical, we fitted our result to a very well established two models, Brooks and Corey model and Von Goetschen model, and these are the results of the assessment of our samples, including the porosity, matrix density, and the mass loss. We can see that the mass loss is very minimal. And these are the imbibition and drainage results of the mass samples achieved for our method. This is for Marcellus samples, and this is for Mancos and Wolfkamp samples. We can see that the results are similar to the standard capillary pressure curves. And the parameterization of our results was done by fitting the results to these two well-established models. And we can see that in this slide, the imbibition test is fitting very well these two models. And likewise, also the drainage curves, they followed they have a very good agreement with these two models, which gave us a confidence in our results. And these are the parameters of the two models achieved by fitting our results to these two models. We compared our one of the parameters that obtained by our study and by previous results, and they are very, which is the pore sorting, or yes, the pore sorting diameter, which is they have a very close agreement with the previous research, but unluckily we cannot find published results on capillary pressure relationship in shales, and we couldn't compare the rest of the parameters with previous studies. And we can conclude that our method, using using a relative humidity chamber to assess capillary pressure relationship in tight reservoir is possible. And we can see that there were negligible hysteresis between imbibition and drainage, which is normal. And there were also very good, the results are following the two well-established models, which is giving us a confidence in our results. Thank you very much.
Okay, thank you, Mr. Hisham, for very good presentation. Okay, now let's open the floor for the question and answer sessions. Let me see if there is any question from the audience. I think there is some technical issue. Okay, there is one question. Does the technique handle the okay, I don't really get the question because they mentioned that does the technique handle the viscoelastic surfactant?
That's for me. Okay. I don't know. I don't totally understand the question, but if you want to incorporate surfactants into the methodology, I believe, yeah, maybe it can be incorporated. But if you want to study like influence of surfactant on this relationship, like capillary pressure, yeah, I believe we can incorporate it on that. By the way, I have a session now. They are calling me in ASAP.
Oh, all
I
right.
don't know
Okay.
if any question I can answer it. But I need to join the other session, I believe.
All right.
Okay.
It's okay. You may join the session, Hisham. Okay. Thank you for your presentation.
Thank you very much. Bye.
All right. All right. Okay. Thank you, Hisham, for the presentation. So, without further ado, I think let's move on with the next presenter, which is Siti Najmi Farhan from Petronas Carigali Sedang Berhad. So she has two papers to present today. Okay, the first one will be on the chronicle of hydrocarbon fluid identification and sampling characterizing downhole fluid properties, highlighting case studies from offshore, international, and domestic Petronas Carigali fields. So let's invite Miss Najmi to the floor.
Assalamualaikum, good afternoon. My name is Siti Najmi Farhan Zulkifli. I am petrophysicist from Petronas Carigali. The title of my presentation for today is The Chronicle of Hydrocarbon Fluid Identification and Sampling, Characterizing Downhole Fluid Properties in Offshore Petronas Carigali Fields. Outline of presentation, I'll start first by giving the objective, and then we're going to see the overview of reservoir fluid sampling throughout the reservoir life cycle. What are the common challenges and pitfalls faced during the sampling? We also get to know what are the common downhole sampling tools and components and how to select them. Some case studies to demonstrate the different applications of sampling probes and what are the impact to the cleanup time required and also the amount of fluid contamination level. And finally, I give the wrap up in the conclusion section. The objective of this presentation is to highlight the technical experiences and also results of the downhole reservoir fluid sampling from operative perspective. It is also to give a brief account on how to plan and execute reservoir sampling job and also to share some of the best practices and lessons learned in the reservoir fluid sampling to date. So overview of reservoir fluid sampling, as much and as best as we could, the sampling should be done as early as possible of the reservoir life cycle. For example, during the exploration, the interest is to know what type of hydrocarbon fluid are present, whether it is oil, gas or water, and how much contaminant are present in the reservoir. During the field development and production later on, reservoir fluid sample can be a very valuable information to help with the facilities design, the reservoir management plan, and also to give some insights on the production allocation matters. So sampling should be attempted as early as possible in the reservoir life cycle, and it should cover both major and minor reservoirs. And the most critical part is to have a pre-job planning in every sampling job that we plan. Some of the challenges faced in reservoir fluid sampling include the time and cost constraint. The longer time we take to pump to get a clean reservoir fluid, the more expensive it becomes because it involves fluid time. So we need to balance between the cost and the time. Detailed sampling procedures must be communicated to all the parties to avoid miscommunication during the operation. And right from the beginning, we must have a clear objective on why we take the fluid samples, whether it is for the hydrocarbon fluid identification only, or is it for the high quality PVT samples job. And the most critical part is to have a proper pre-job planning to avoid the loss of opportunity in acquiring downhole sample due to the improper planning and also due to the improper selection of the downhole tool and equipment. Throughout the years, we have seen many changes and many evolutions in the reservoir sampling downhole components. Starting from the early 50s and 60s, where the first sampling job was executed up until now, there are many new technologies have been introduced to the industry. And some of the most common fluid properties sensors being used in our operations today include density sensor, viscosity, gas-oil ratio or GOR, CO2 sensor, H2S, capacitance, refractive index, and also hydrocarbon fluid composition. When it comes to the selection of downhole tool components, many factors affect the selection, and these include the borehole size, borehole stability, the job objectives, the fluid properties, whether it involves sour gas such as CO2 or H2S, and what is the amount of fluid contamination level that we want to achieve. So all these factors play a key role in the selection of the probe selection that we want to deploy downhole, what type of pump and what's the rating for each we want to install downhole, how many sample bottles that we want to utilize, and also what are the type of fluid sensors that we want to include for the downhole measurement. So moving on to the case study number 1 involves 2 offshore deep water wells environment. So based on the log interpretation, rock quality in well number 1 is better compared to rock quality in well 2. Well number 1 utilized 3D radial probe, while well 2 utilized focus sampling probe. 3D radial probe in well 1 is observed to give a faster cleanup time, is about 1.6 hours, compared to the focus sampling probe in well 2, which takes longer cleanup time, about 7 hours. Case study 2 involves sampling in the laminated reservoir in 2 wells. Based on the log interpretation, these 2 wells have a similar reservoir rock quality. Reservoir X in well 1 utilized elongated or elliptical probe for sampling, while reservoir Y in well 2 utilized extra large diameter or XLD probe for the sampling. For the hydrocarbon fluid identification, both type of probe in both wells give a pretty much similar cleanup time, about 25 to 29 minutes of cleanup for good reservoir quality rock. For the poorer reservoir quality rock, it can take up to 40 minutes for the cleanup time. In terms of fluid properties, comparison between the downhole measurement and the PVT lab measured properties, it is observed that the elliptical probe is giving a much narrower differences in terms of density, viscosity, and CO2 reading, while the XLD probe is giving a much wider differences in this fluid properties measurement. In this case, elliptical probe is giving about 1% to 5% difference, while the XLB probe is giving difference between 3% up to 74% differences accordingly. Case study number 3 involves the application of focus sampling probe in a slim 6-inch hole section. For fluid identification purpose, 2 stations were identified in the well. First station involved gas-bearing sandstone with a permeability about 49 millidasi and also porosity about 20%. Second station involved oil hydrocarbon fluid identification with the same quality of rock. It is observed that with this kind of rock quality, it takes about 3.8 hours of cleanup time to reach a low, less than 5% contamination level. In other reservoirs which utilize the same focus sampling probe, at poorer rock quality, it takes much longer time for cleanup, which is about 5 to 7 hours, whereas in a much better rock quality, it takes about 2.5 hours of cleanup compared to the baseline about 3.8 hours. We can also further determine the amount of reservoir fluid contamination in the lab. So these figures in the middle show the mud sample hydrocarbon composition, whereas the figures on the right shows the hydrocarbon composition for the crude oil. So taking a direct subtraction for each of the component in the composition, we can actually derive and quantify the amount of the filtrate contamination, and in this case, it's less than 10%. Case study number 4 sees the deployment of 3D radial probe in 2 hydrocarbon fluid identification stations. The first station involved gas-bearing sandstone with a good porosity and permeability readings, while the second station involves the depleted oil reservoir at a much lower porosity and lower permeability reading. Regardless of the fluid type and regardless of the rock quality, it is observed that this 3D radial probe is giving a pretty much similar of cleanup time between 28 minutes to 33 minutes respectively. So it is proven that 3D radial probe is less sensitive to the tight formation and it gives an advantage of faster cleanup time in the tight reservoir rock. Case study number 5 sees the application of the dual packer sampling tool, whereas in the tool itself, it has 1 meter spacer which separates the packer number 1 and packer number 2 as shown in the photo above here. In overall, this dual packer type configuration tool gives the longest time for cleanup. For example, in a case and perforated condition, it takes about 5 hours of cleanup time, whereas in the open hole section, in average, it takes about 3 hours of cleanup time along the low porosity and low permeability interval as shown in the log below here. Case study number 6 is the application of the 3D radial probe, both with and without the cleanup flow lines. So the prolific oil-bearing sandstone here at the upper part, the sample was acquired using 3D radar probe without cleanup line, whereas the bottommost two samples were acquired using a 3D radar probe with dedicated cleanup flow lines. Lab analysis indicates that almost 0% contamination were achieved for both types of samples. Comparing between the downhole measurement in fluid properties and also lab-derived properties, it is observed that the difference in viscosity reading for those samples acquired with the 3D radar probe with dedicated cleanup flow line is much lower than the sample acquired using the conventional 3D radar probe without cleanup flow line. Case study number 7 offers an alternative in the reservoir's downhole fluid sampling, whereas the sample is acquired during the drilling time itself instead of waiting after the drilling is completed. It is observed that the amount of cleanup time to see the reservoir fluid coming into the wellbore is about 30 minutes. So in this case, sampling while drilling offers an advantage in terms of faster cleanup time due to less mud invasion during drilling as compared to after drilling. So to summarize, here are some of the best practices in reservoir fluid sampling. Pre-job planning is critical to select the best and the fit for purpose downhole to configuration. Pre-job modeling is also critical to determine the cleanup time required and what is the amount of fluid contamination level that we want to achieve. Parameters such as pump rate, pump volume, and what type and how much pressure down to be applied can also be simulated. Do we need special coating for the equipment if there is any sour gas presence? And also in certain cases, we can also plan to obtain a reliable fluid sample in a sluggish flow condition. So in conclusion, pre-job planning is highly critical to obtain a representative reservoir fluid sample, and it is also critically important to know the job objective upfront to plan for the job properly. There are many factors affecting the quality of a reservoir fluid sample. Some of them include the reservoir quality, the reservoir characterization, the hole size, and also the flow dynamics that are involved during the sampling job. Throughout the case studies, we have seen many types of different probes being used, and in essence, 3D radar probe or the focus semi probe offer the best quality to get the most cleanest reservoir fluid. Tight formation is best attempted using dual packer or 3D radar probe, while laminated sand is best attempted using the elongated or elliptical probe. So technology in the downhole reservoir fluid sampling will continue to evolve, and based on our technical experiences and lessons learned gathered so far, it is hoped that all this new technology can help to further enhance or improve the reservoir quality of fluid sample that we have, and also to improve the operational efficiency in the near future. I would like to acknowledge Petronas Carigali management and technical team for their support and approval to present this paper in this conference. Thank you.
Okay, thank you, Ms. Najmi, for a very good presentation. So I think there are questions from the floor. Okay, the first one, you are presenting different case studies of sampling pre and during the acquisition. The intention is to measure the sample integrity. What are the conclusions or the lesson learned from this scenario? Okay,
Right. Thank you very much to the audience who asked this question to me. First of all, thanks again for inviting me to this session. And to answer this question, what are the lessons learned or conclusion derived from all these experiences so far in street sampling? The first thing I will say is it is a job by design, right? It does one fit or one size doesn't fit for all categories. We need to really design and plan. Selection of the hardwares and also sampling configuration is a must, depending on the job objective. For example, is it only for hydrocarbon fluid typing, or is it for the high quality PVT sample that you want to acquire downhole? It must come together with a very detailed planning. And also hardware selection, such as the probe type, right? In this case study, we have seen a lot of probe types like single probe, elongated probe, dual packer, 3D radar, and they all serve different objective and different applications. For example, if you are targeting, sampling high PVT quality sample in a very laminated, very tight rock, or a very challenging environment, then Pre-job simulation is a must, and the hardware that you choose is also must fit for purpose. And for example, we talk about this thin lamination sand, where the elongated probe is the most suitable. Tight rod, you can either choose dual packer probe or even focus sampling probe. So things like that must be taken into consideration. Yeah. So lessons learned so far, this job must go by design. It doesn't work based on the template. It doesn't work based on the one size fits for all. Yeah.
Okay, all right, thank you. I think you also have explained what you call the second question, which is can prop configuration has the impact mentioned in study? All right, okay, then, now let's move with the next last questions. How the total clean up time affect the sample contamination?
Right. By logic, the longer time that you pump, the higher volume that you pump for cleanup, the more clean the sample would be. But
Yeah.
this cleanup time has to be balanced with the rig cost and time, yeah? Because the longer we pump, of course, the cost incur will be higher.
Yeah.
So for that to balance between the cost and the time and the sample quality that you achieve, it must be pre-modeled, it must be pre-simulated before the job. Yeah.
Okay.
So it comes together with detailed planning, yeah, and it comes together with the fit for purpose hardware selection to achieve the minimal time, but at the same time you achieve a good quality sample for analysis.
Is there any rule of thumb for that?
Yes, in the conclusion that you see, for example, the probe time, yeah? Laminated sand, you go for the elongated probe.
Yeah.
Tight rod, you go for the dual packer or you go for the 3D radial probe.
Mhm.
And if you are aiming to get a high quality or PVT type of sample, you go for focus sampling probe technique.
All right. Okay, thank you, Ms. Najmi, for your time. So I think let's proceed with your next presentation. Okay, so the next presentation from Ms. Najmi will be on the petrophysics of complex lithology, unlocking the potential through real-time mineralogy, measurement, native state core analysis, advanced fluid characterization, and integrated formation evaluations.
Assalamualaikum and good afternoon. My name is Siti Najmi Farhan-Zulkifli. I am petrophysicist from Petronas Carigali, and the topic for my presentation is the petrophysics of complex lithology, unlocking the potential through the real-time mineralogy analysis, native state core analysis, advanced fluid characterization, and also integrated formation evaluation. Outline of presentation, I'll start first by giving the objectives and then moving on to the overview of the complex lithology environment, what are the common challenges usually faced in the complex lithology interpretation, how to achieve the synergy or balance between the rock and fluid properties in complex lithology environment, and then moving on to the case studies to demonstrate some of the best practices and technology application to evaluate the complex lithology reservoir, and finally I'll give the wrap up in the conclusion. So the objective of this presentation is to highlight some of the best practices of data acquisition approach and how can certain technology can help to reduce the uncertainties in the complex lithology environment interpretation, to share some of the technical challenges and how the integrated approach can help, and also to highlight the importance of data integration in minimizing the interpretation uncertainties. So overview of the complex lithology. A complex rock is usually made up of more than 3 minerals, and some of the common minerals present in the earth include salt, feldspar, glauconite, phreatic sand, limestone dolomite, and also volcanic ash. Presence of these minerals in abundance in the earth can actually impact the log response, especially the density, the neutron, and also resistivity logs. Active diagenesis and minerals alteration can also happen even after the rock has been deposited, and some of these minerals are closely related to the elements present in the earth, such as the silica, the calcium, the potassium, magnesium, aluminium, and also sulfur, to name a few. So these are some of the challenges commonly faced during the complex lithology interpretation. We need to quantify the amount of each mineral present in the rock and also to determine which minerals are more dominant compared to the rest. Each mineral is also has a specific matrix density. With the combination of multiple minerals present in a rock, we need to find a variable or a composite matrix density for each of the mineral in order to compute an accurate porosity of the rock. Permeability might not show a direct relationship with the porosity in the complex hydrologic environment. Hence, the log-derived permeability must be calibrated with the core data and also permeability derived from the well test. Certain minerals are also conductive, such as pyrite and siderite, and in overall, this can pull down the resistivity impact, which can already mask the hydrocarbon presence in the reservoir. Certain minerals also show some compatibility and different affinity to the oil and water in the rock, which makes the determination of the fluid contact or free water level across the reservoir becomes more complicated. In terms of method growth, presence of complex minerals also can make the distinguish between pay and non-pay zone becomes more difficult to be distinguished, and also for the gross rock volume, due to the multiple layers of stratigraphic presence, and also different depositional sequences. So in essence, achieving a balance or synergy in reservoir characterization between the rock properties and fluid properties are highly critical in the complex hydrologic environment. So here in the middle is metaphysical methodology on how to interpret the complex hydrologic environment. In each of the steps here, calibration and validation of the core data is a must, and the application of certain technology in the data acquisition can actually assist to minimize the uncertainties in the interpretation. For example, application of the elemental capture spectroscopy log can actually identify the types of mineral present in the rock. Application of the nuclear magnetic resonance or NMR log can also identify the total porosity independent of lithology and matrix. Application of the real-time mineralogy analysis based on the X-ray diffraction, XRD, and also X-ray fluorescence, or SRF, based on the cuttings data, can also identify the minerals present in the rock. And application of the downhole fluid sampling and downhole fluid characterization can also assist in terms of identifying the in-situ fluid properties such as the density, the viscosity, the gas-oil ratio, the fluid compressibility, the bubble point pressure, and also hydrocarbon fluid composition. Moving on to the case study, so case study number 1 involves field A, which is located in offshore deep water environment. 2 wells have been drilled so far in this field. Each of the well, the target reservoirs lie below the complex hydrology, which comprise of the halite, sylvite, and also anhydrite salt. Extensive data acquisition program has been planned in each of the well, and the table on the right here shows the list of data acquisition has been conducted, such as the triple combo logging, sonic and image data, elemental capture spectroscopy log, NMR logging, vertical seismic profiling log, and also sidewalk core data. In well number 2, a total of 43 meters of conventional core barrels was also acquired. Based on the core photo and CT scan images from the conventional core in well number 2, it shows that the formation is highly heterogeneous. Some fractures are present where most of the fractures are filled with dolomitic veins. This is further confirmed with the thin section description where most of the open fractures are actually filled with this dolomitic vein. Heavy mineral study was also conducted in this well where it proved the presence of minerals such as titanium oxide or rutile and also zircon. So the presence of these heavy minerals can actually increase the reading of the density log, and it can actually impact the porosity computation of the rock. In terms of log evaluation, due to the complexity of the rock in the formation and also due to formation tightness, all the log-derived properties such as porosity, permeability, water saturation, and lithology need to be calibrated with the core data. So the log display below here shows a good to moderate validation between the log-derived properties and the core data, as well as the real-time mineralogy analysis based on the cuttings. Due to the complex minerals present and the formation tightness, identifying hydrocarbon presence in this type of rock is also difficult. Hence, it is highly recommended to deploy downhole fluid sampling and also downhole fluid characterization in order to determine the in-situ fluid properties such as the density, viscosity, GOR, bubble point pressure, the compressibility, and also hydrocarbon fluid composition. Image log was also deployed and run in this well with the objective to determine the unique sedimentary features, identify the direction of sand deposition, and also to examine the possible of lateral sand connectivity in between the wells. As a result of integrating of all this available subsurface data, additional 23% of hydrocarbon pore volume, which translates to additional hydrocarbon in place, was successfully recorded. Case study number 2 involves well B, which is mainly characterized by the thin sand shale lamination. Extensive data acquisition has been planned for the well, which include the deployment of the triaxial resistivity to determine the horizontal and vertical component of the formation resistivity. The NMR log was also logging to determine and to identify between bound water and the movable hydrocarbon portion. An image log was also run to further distinguish between pay and non-pay zone. As a result of integrating of all these subsurface data, additional 48% to 55% of hydrocarbon in place volume was successfully recorded. Case study number 3 involves well C, which is drilled through a complex dolomitic limestone layers. In this well, extensive subwall core data and also real-time mineralogy analysis based on the cuttings, SRD and SRF analysis was conducted. And the logs displayed here shows how the petrophysical interpretation in terms of lithology and mineralogy has been calibrated very well to the core data as well as the real-time mineralogy analysis. Case study number 4 again involves well D, which is drilled through a very complex formation layer, which is comprising of the salt, the shale, the marly limestone, and also the bituminous sand. Based on the seismic data over here, throughout the salt interval, the seismic response or signal is very weak. And based on the cuttings description for the well, it is also observed the bituminous fragments are present in between the sand grains. As a conclusion, we have seen that additional hydrocarbon pore volume, which translates to additional hydrocarbon resource in the range of 23% to 55%, was successfully recorded as a result of using integrated formation evaluation in the complex lithology environment. Lithology and mineralogy interpreted from the logs must be calibrated with the core data. In terms of porosity, NMR log porosity and also porosity determined using variable metric density give a closer match to the core porosity compared to the single approach of using single matrix density. Permeability is best to be determined from core as well as effective permeability from the well test data. The log draft permeability must be validated using these two sources of information. In terms of water saturation, it is observed that using variable cementation exponent or variable M approach is giving a closer match to the core water saturation instead of giving a single M value. 3D radial probe or focus sampling probe is giving the best quality of reservoir fluid and the lowest level of fluid contamination level. Last but not least, the deployment of image log is highly recommended in this complex hydrology environment to give information on the sedimentary features and also to determine the direction of the sand deposition and also to examine the possible of lateral sand connectivity in between the wells. I would like to acknowledge Petronas Carigali management and technical team for their support and approval to present and publish this paper in this conference. Thank you.
Okay, thank you, Ms. Najmi, for the presentation. So, okay, let's go with the question and answer session. So there is one question. To enhance the complex lithology evaluation, one may need to have sufficient data, quality and quantity. How this aligns with the current study?
Right.
Yeah,
Thank
Najmi.
you for the question, and audience and host. Yeah, in this paper, what we present and what we demonstrate is the integration of many dimensions data acquisition, ranging from seeking the image, seeking the fluids, characterizing the rocks and the cores. So we look at multiple dimension of formation evaluation perspective. So when it comes to complex lithology, you cannot only focus at one dimension and ignore the others, right? So it won't give you the complete picture of the whole reservoir characterization work or study. So what we do here, of course, bound with the cost as well. And we try to optimize and balance between the cost and the data acquisition. We plan the job properly, and we only take a certain critical information that must as compared to what we need or nice to have. Yeah. So balance between the two and integrating for all the data available to us, even in real time or even post job, we acquire and we analyze each of the data in detail, and that helps us to make up, to conclude what's really there in the downhole in the complex hydrology reservoir.
Okay. All right. Thank you. And there is another question. Any updated info about the most critical lab data?
Okay. Right. So
QC.
petrophysics, yes, petrophysics is always has numerous parameters, I would say. So the most common petrophysical parameters will include like porosity, permeability, water saturation, and even lithology, right? Whether it is sand, shale, or even complex minerals. So in terms of lab data, the one that we commonly look at is, of course, like porosity from the core, permeability from the core, saturation from the core, and even lithology fraction or mineralogy component from the core. So that components or that results being analyzed and determined from the core. We use that data to validate and calibrate back with our interpreted from the logs.
Okay.
Interpretation from the logs. And also, not forgetting, it's not only rocks that we look at. We also look at the fluid. Yeah, because the rock itself will provide you the storage for the fluid for the hydrocarbon to be stored. So we also look at the fluid, and in terms of lab data, we look at the PVT data for the fluid analysis, and that PVT data, I'm sure that you see the previous presentation just now talking about the samples. So that's where we characterize the fluid. So we lab data results with the fluid that you acquire downhole from those measurement fluid sampling. So we look at both that dimension, both rock and fluids for the complex lithology.
Okay. Thank you, Manajmi, for your very, detailed answer. I like the way you answer the questions, very detailed.
Thank you for the question to the
All right.
audience.
Okay, thank you, Najmi. All right, I think that's all for the session. Okay, so ladies and gentlemen, we have to come to the end of this technical session. So on behalf of Icoget, I would like to thank each and every one of you for your participation and patience throughout this session. So please do not forget to visit the exhibition booth by our sponsors and co-sponsors. If you have any comments or queries on this session, please feel free to leave your thoughts in the live Q&A chat box. So thank you very much and do have a nice day ahead.